Hello, this is part one of the t-test, and the t-test is basically something you use in a situation where you've got two samples like these two here that aren't that different from each other, but there might be a difference, and the t-test will tell you if that difference is statistically reliable or not. Before we get underway, I'm going to revise a couple of topics from last week that are going to be helpful for understanding the t-test. Okay, so the first revision topic is the null hypothesis and the associated p-value. So remember that in a simple experiment, your null hypothesis is just that both samples are samples from the same population, and by population we mean population of schools, not population of people. So for example, population of reaction times, and the assumption is of course that the samples were selected randomly from that same population. So given the assumption of the null hypothesis being true, what statistical tests do is calculate the probability of the observed difference, or a larger difference, between two sample means occurring. And that probability is what you will hear referred to as the p-value. Okay, so this is a complicated phrase. It's not that difficult really. The sampling distribution of the difference between two sample means. Now, you constructed a sampling distribution for a single sample mean in your workshop, but to get a sampling distribution of the difference between two sampling means, what you need to do is select not one sample from the population, but two samples, each selected randomly. The samples are in pairs. You calculate the difference between the means of the two pairs of samples, and you can use those to create a frequency histogram. And in the ideal case, you have a very large number, or an infinite number, of pairs of samples, so you get a nice smooth frequency histogram. So that frequency histogram will be normally distributed, and it will have a mean of 0. Now notice how that differs from the sampling distribution of a single sample mean. It has a mean of 0 because, given that the samples are all from the same population of schools, on average the difference between any two samples would be 0. Of course, if it was a sampling distribution of a single sample mean, it would have a mean equal to the population mean. So because the sampling distribution of the difference between two sampling means is a normal distribution, that gives us some useful properties. When the null hypothesis is true, 68% of differences between two samples lie within plus or minus one standard error of 0. Remember that the standard error is the standard deviation of a sampling distribution. And given the properties of normal distributions, which you can remind yourself of by looking back at the diagram of the standard normal distribution from a couple of lectures ago, 95% of differences between pairs of sample means will lie within plus or minus 1.96 standard error of 0. Now, to calculate the standard error, you would need to know two things. The sample size. Remember that the standard error of a sampling distribution halves every time the sample size quadruples. You'd also need to know the standard deviation of the theoretical population of different schools. That's not usually known, but what we have in the t-test that I'll show you later is a formula for estimating that standard error. And remember that this all assumes that the pairs of samples came from the same population. if the pairs of samples were from different populations, then the sampling distribution would not anymore have a mean of 0. But we're not really interested in that case because it doesn't really happen very often that we have access to that information. Okay, so let's move on to the t-test. What the t-test will do is compare two sample means to check whether there is a statistically significant difference between them. This is covered in chapter 9 of the textbook, and I also put some references to other parts of the textbook up in this little grey section of my slides where appropriate. So today we will cover the meaning of the t-statistic, which is something that is often forgotten. We will look at how to calculate t for what's called an independent samples experiment. We'll look at how t is converted to a p-value under the assumption that the null hypothesis is true, and we'll finish up by looking at a tricky little topic called degrees of freedom. Okay, so if you're just going to remember one thing about t-tests, then this is the thing to remember: that t is a statistic that is bigger when it's less likely that two samples were randomly selected from the same population. When t is quite a bit bigger than 1, we can be quite confident that the two samples were not selected from the same population. So maybe when you get a t value of 2 or 3, you could start to get excited. Okay, this is the general formula for t-statistics. There are a number of different t-statistics for different situations, but they all follow the same general form. The numerator, that's the top part, is variation in the dependent variable due to the independent variable, and the denominator, that's the bit underneath, is some estimate of measurement error. Now, because t is a ratio, one thing divided by another, it means that as the number on the top, the numerator, gets larger, that's going to mean it's less likely that the two samples are from the same population. Makes sense, really. Bigger effect of the independent variable is less likely to be due to just measurement error. But as the denominator, that is the measurement error, increases, you're going to be dividing by a bigger number, and so t is going to be smaller, and that means it's more likely that the two samples were from the same population. So let's expand that formula a little bit. T is sample mean 1 minus sample 2 mean divided by measurement error, and measurement error is higher when the standard deviation in the data is higher, and it would also be higher when the sample size is smaller. So, further notes on understanding the meaning of t values. I like to think about t in relation to z, helps me understand the difference. So let's remind ourselves the meaning of z scores. If we have a man who is quite tall, 6'6", he might get a z score of 2.5, and that's because the difference between his height and the mean height in the sample or population is equal to 2.5 times the standard deviation in the distribution. So you'd have to add 2.5 times the standard deviation to the mean in order to get his mean height, and therefore the units of z-scores are standard deviations. So what's the meaning of a t-statistic of 2.5? This time the 2.5 means that the variation in the dependent variable that is caused by the independent variable is 2.5 times as large as the estimate of the measurement error in the experiment. So immediately we can see that if t is less than 1, that means that measurement error is larger than the effect of the independent variable, and so probably we're not going to be able to conclude much positive about the effect of our experimental manipulation. So T statistic is a ratio of the effect size to error, and the units it has are units of measurement error, or more specifically standard error. Now, something to get out of the way early is that the T statistic can take negative values, but these negative values have no special meaning. Whether T is negative or positive just depends on which way round you subtract the sample means. If you subtract the larger sample mean from the smaller sample mean, you'll get a negative T value, but if you do it the other way around, you'll get a positive T value. Okay, let's have a more exact description of the meaning of T. T is sample mean 1 minus sample mean 2 divided by the standard error estimate. So a T statistic of 2.5 means that variation in the dependent variable due to the independent variable is 2.5 times bigger than the standard error of the sampling distribution. And as I said on the last slide, the units of the T statistic are standard errors. Okay, let's look at the formula. Formula looks a bit scary if you kind of try and take it in all at once, but if we break the formula down, it's actually quite easy. Before we look at the formula, a couple of points to make. One of them is that different people write the formula different ways. This is a formula that can be rearranged. Some people write it using the variance instead of the standard deviation, but I write it using the standard deviation because I think it's easier to understand. The other thing to say is that this denominator part of the equation that I'm highlighting here with the laser pointer is the estimation formula for the standard error of the sampling distribution of the difference between two sample means. And you could go back and compare it with the estimation formula for the standard error of a single sample mean. Now, so the numerator is just sample 1 mean minus sample 2 mean. The denominator, the estimate of measurement error, is broken into two parts, one for each sample. So if we look at the left hand part, we see that we take sample 1 standard deviation, that's the people in experimental condition 1, and we divide that by the square root of the total sample size combined across the two experimental conditions. Now remember, the reason we use the square root is because it helps us get at this relationship of the sampling distribution whereby the standard error of the sampling distribution halves every time the sample size quadruples, and the square root is just a convenient way of making that happen. So then we do the same thing for the second sample. We look at its standard deviation, that's for the people who did the second experimental condition. Again, we divide that by the square root of all the people in the experiment, and then we add together our two parts of the standard error estimate. That gives us our standard error that we can divide the effect size or effect of the independent variable by. And that's just a reminder there that of course to appear that the denominator, that's the bottom part of this formula, is your estimation formula for the standard error of the sampling distribution of the difference between two sample means when two samples are drawn from the same population. In other words, that the null hypothesis is true. Remember that what we're trying to do in statistics often is set up a null hypothesis and then prove that it is wrong. So let's look at some worked examples. In this example, we're going to imagine that some researchers have hypothesized that daily supplementation with 200 grams of blueberries is going to improve cognitive performance, and that predicts that there will be better exam performance than in a control condition that matches the calories in the blueberries and the vitamin C in the blueberries. So the researchers think that it's some other ingredient of the blueberries, namely the flavonoid content, which is likely to cause the improved cognitive performance and therefore exam scores. So the researchers recruit 60 participants and they randomly divide them into two groups. So we know that the participants initially are from the same population, because 60 people were randomly selected from a population and then divided randomly into two subgroups. One half of the original sample will be given blueberries, the other half the control, and the dependent variable will be exam scores. Now the results of the experiment show that the blueberry group get average exam scores of 57.47% with a standard deviation of 10 and a bit. And the control group, they don't do as well. Average exam score 50.77, standard deviation just under 10. So on the face of it, there's some evidence there that the blueberries had an effect. So let's plug those numbers into our formula for calculating the t statistic. The sample 1 mean, that goes here. Sample 2 mean, that goes here. Sample 1 standard deviation, that's in there. Sample 2 standard deviation is here. And both of those get divided by the sum of the two sample sizes. And that results in a t statistic, if you work it out, of 2.58. And you know from what I said earlier that is quite a large t statistic. The effect of the experimental manipulation is more than twice as big as our estimate of measurement error. Okay, so to help us understand the t formula and how it works, we'll consider a few examples of different variations on the results of this example experiment. So we're going to think about what happens to the t if the samples are more variable, i.e. a higher standard deviation, or less variable, i.e. a lower standard deviation. This is just a diagram to visualize that situation where we haven't changed the means in the samples, they're staying the same. Look, the green could be our control group here and the blue could be our blueberry group. The mean stays the same. In our original example we have medium variability, medium size standard deviation. If we make the samples more variable, we can intuitively see that that difference between the two means kind of looks smaller now. We wouldn't trust it as much, would we, when there's more variability in the data, because it's small in relation to that variability. If, on the other hand, there was much less variability in the data, such that, you know, these two histograms hardly even overlap, well, at that point we probably wouldn't even bother doing the statistics, to be honest. In the sense of doing the t-test, that is. Of course we still calculate the means and the standard deviations. So let's look at the math for this. Up here is the situation that we started with, the medium variability. And let's bring in some new numbers now. Look at that. Here the standard deviation has increased from 10.33 to 18.1, so it's a more variable sample. Also increased the variability in the second sample. Also increased the variability in the second sample, see that here, and this results in a reduction in the size of the t-statistic due to the increased variability. Note that the sample size bit stayed the same. So now the effect of the blueberry drink on the exam scores is only 1.5 times bigger than our estimate of measurement error, and we wouldn't be too confident anymore that the blueberries really had an effect. Okay, let's go back to our original example. That's the numbers up here, and ask ourselves what happens when you vary the sample sizes. And we'll look at the maths for what happens if we keep everything else the same, that is, keep the variability the same, i.e. the standard deviations, and keep the effect of the independent variable the same, but reduce the sample sizes. Let's bring in the new sample sizes. I've reduced the sample sizes from 30 and 30 to 11 and 13. This brings out an important point actually as an aside. For the independent samples t-test, there is no need to have equal numbers of participants in the two groups, although they should not be dramatically unequal. So the result is a reduction in the t-statistic. Here we've got the same number of participants, we've got less participants, but we've got the same variability as in the original example and the same effect of the experimental manipulation, but we no longer have as much confidence in the result, and that's because of that relationship of standard error halving every time sample size quadruples. Of course it does get smaller in a smooth way, it doesn't just suddenly halve at the point where the sample size quadruples. So let's look at another thing that we haven't changed yet in the example. Let's look at what happens if we just imagine that the blueberries had a smaller effect. So let's imagine the blueberries only had half as much effect on exam scores as in the original example. So here I'm leaving the score for the control group the same, but now the group that eat blueberries, they only score 54.1 instead of 57.47. So rather than a 7% improvement in exam scores due to blueberries, it's about 3.5%. The result of this is that t is 1.29, which is exactly half of what it was before. Simple really, halve the effect size, halve the t-value, double the effect size, double the t-value. So for our final manipulation of the original example, we will look at what happens to t when we halve the effect of blueberries on exam scores, but we also increase the sample size to 120 in each group. So two effects at once are being changed. You might want to pause the video for a minute and have a think and see if you can work out what the value of the t-statistic will be. So let's bring in the numbers. There is our reduced score for the blueberry group compared to what we had in the original example. And here are our quadrupled sample sizes. And I'll now bring in the value of t, which as you can see is unchanged. That's because I've halved the value of t by halving the effect size, but then I've doubled it by quadrupling the sample size. And there's a lesson in this, because if you see, a big t statistic like that, but the sample size is really big, Well, it might not necessarily mean that the actual effect is very large or important. It's just that they've got a lot of power in their experiment due to the big sample size. When there are big sample sizes, you need to also look at a statistic called the effect size that I will cover next week in order to assess whether the effect is important as opposed to statistically significant. Okay, let's move on to look at how we convert a t-statistic to the all-important p-value. We already know that when t is bigger, that means a pair of samples is rather unlikely to be obtained just by random sampling from a single population. But we need to be more exact. We need to actually calculate a value that we can report. So if the probability distribution of t when the null hypothesis is true was Gaussian, i.e. a normal distribution, then converting t to p would be pretty easy. Values of t larger than 1.96 would only occur 5% of the time when the two samples were from the same population of schools. And so we could say that whenever t is greater than 1.96, p is less than 0.05. And based on the rules we looked at last week for setting the trade-off between type 1 and type 2 error, a p-value of less than 0.05 could be taken as support for the hypothesis. However, the t-statistic is not actually normally distributed when the null hypothesis is true, which makes it a bit more complicated. However, the principle is just the same as for the normal distribution curve and the areas under the curve that correspond to the different probabilities. In fact, there is a test called the z-test, which is based on the normal distribution instead of the t-distribution, but the z-test only works properly when the sample size is 30 or larger, which is why we prefer the t-test, because it allows us to get accurate estimates of the p-value for small samples. Okay, so let's see how the t-distribution differs from the standard normal distribution. How it differs depends on something called the degrees of freedom, which you'll often see abbreviated as df. The degrees of freedom are just calculated based on the sample sizes. So in the example we're working with today of the independent samples t-test, it's just n sample 1 minus 1 plus n sample 2 minus 1. So in our blueberry example, the degrees of freedom would be 58, because that 30 minus 1 plus 30 minus 1 is 58. So let's look at an extreme example when there are only 2 degrees of freedom in a t-test. And you would get 2 degrees of freedom if, for example, sample 1 only had 2 people in it and sample 2 also only had 2 people in it. So in this graph on the left, the blue curve is the standard normal distribution that you might recognize, and therefore the x-axis is units of standard deviation for the blue curve, and the y-axis is the proportion of the area under the curve. Now for the red distribution, which is the t-distribution, the x-axis is now units of t-statistic rather than units of standard deviation, or z. And you can see that these two curves have quite different shapes, and most importantly the proportion of the area under the curve will be different for the two curves for a given value on the x-axis. And if we think about that important value in the standard normal distribution of 1.96, or let's just call it 2, where in the standard normal distribution only 2.3% of cases within the distribution fall are greater than 2, for t, that's 14.7% of cases fall into this area greater than 2 when there are only 2 degrees of freedom. And what this does is it has the effect of making the t statistic much more conservative than the z statistic or standard normal distribution when the sample sizes are small. And that's important because it stops us making claims about statistically significant results based on very small samples unless the effect really is very reliable. And the reason for that is because remember that it's this proportion of the area under the curve that is greater than the value of the statistic, which is equal to the p-value of that statistic value occurring if the null hypothesis was true. Okay, let's look at the example where degrees of freedom are 4. Blue is still the standard normal distribution. Green are the curves for degrees of freedom 2 and 3. Red is the curve for degrees of freedom 4, which is what you could get if you had, for example, sample sizes of 3 in both experimental conditions. And you can see that the red curve is starting to look a bit more like the blue curve compared to the 2 green curves. And now the proportion of the area under the curve that is greater than 2 is down to 5% for the t distribution compared to 2.3% for the z distribution. Remember that when degree of freedom was only 2, it was about 14% of the area under the curve for the t distribution. So what we're saying is that a t statistic of 2 is much more likely to indicate a significant result in a sample size of 4 than it is in a sample size of 2. That's a sort of intuitive version of it. Of course, 4 degrees of freedom is still a very small amount. If we looked at the case where the degrees of freedom was about 20, then the blue and red distributions for the standard normal distribution and the t distribution would be looking fairly similar, and the percentage of the area under the curve that was greater than 2 would be getting fairly similar. Once you get past a sample once you get past 30 degrees of freedom, the t distribution and the standard normal distribution are identical, and the z-test and the t-test are effectively the same. The proportion of area under the curve greater than a particular value of the statistic, such as 2, is the same. Now, that might have all sounded a little bit complicated on the last couple of slides. Fortunately, in order to convert t to a p-value, that's actually done for you by the computer software SPSS that you'll be learning to use in your workshops over the next couple of weeks. SPS, in fact, calculates the t-value, calculates the degree of freedom. It actually, in the background, generates the correct t distribution under the assumption of the null hypothesis being true. It calculates the proportion of the area under the curve for which t is larger than the t in your experiment. If you're doing a two-tailed hypothesis, this includes both negative and positive t. And that proportion of area under the curve is equal to the probability that the difference you observed due to the independent variable or a bigger difference would occur if the 2 samples were randomly selected from the same population. And remember that if the probability of 2 samples coming from the same population is low, that is indirect evidence that they actually come from different populations. Okay, so let's just remind ourselves again about interpreting and using the p-value that you get out of the t-test and lots of other statistical tests that you'll be looking at over the course of the next 2 years. Whenever the p-value is less than 0.05, which is the same as saying 5%, then that gives you enough evidence to reject that pesky null hypothesis. Remember, the null hypothesis is like a criminal who's accused of a crime, and you put them in the court, but they are innocent until proven guilty, and you need quite a lot of evidence to prove them guilty. It's not just enough to have a bit of evidence. It has to be beyond all reasonable doubt, and that's why we insist on having p less than 0.05 to reject the null hypothesis. Once the null hypothesis is rejected, we can say that the two samples came from different populations of scores, and from your scientific viewpoint you could say that the independent variable had a real effect on the dependent variable, and you may write in your lab report that the hypothesis was supported. Finally, let's finish by saying a little bit more about degrees of freedom, which is covered in the textbook in this little box here, Jane Superbrain 2.2. So basically, degrees of freedom are the number of elements in any calculation that are free to vary before the result becomes fixed. So, for example, if you know that you have 4 numbers, and you know that those 4 numbers have a mean of 10, you can't say anything about what any of the 4 numbers are, because there are an infinite number of sets of 4 numbers that have a mean of 10. But if you were given the additional information that the first 3 numbers in the set of 4 are 8, 9 and 11, then in order to get a mean of 10, the 4th number has to be 12. If, on the other hand, you were only given the information that the first 2 numbers were 8 and 9, and 2 numbers remained unknown, then there'd still be an infinite number of possible pairs of numbers that could make up those 3rd and 4th places in the set. So that wouldn't be enough for you to specify exactly the 4th number. Anyway, I think you can see what I'm getting at here, which is that this calculation that I've been talking about has 3 degrees of freedom, because once you know 3 of the numbers, the 4th one is fixed. So that's the end of t-test lecture part 1. Next week I'll be talking about the different types of t-test, effect size and some other topics.